so let me come to now to yeah, thank you. Yeah, to the 3D n equal 2 surface. And their dualities. So this is, in a sense, a sort of a conventional introduction to 3D n equal 2. So I changed the gear very, very much, in fact. So in the last talk, I emphasized non-conventional thing, etc. But here, I try to follow most of all the 90s literature in the 90s. Right. So as I said, I'm going to assume the first several chapters of this paper. And I want you to superspace. That's not too much important for describing physics, but it's useful and safe sometimes. So I use that. Now, so what's this 3D n equal 2 supersymmetry? In fact, so the nice way to say that is that 4D n equal 1 3D. And well, superspace, for example. Maybe superspace is a more accurate way. Superspace. And compactify on S1. And then we obtain 3D n equal 2 superspace. And this is very good because you can start this 4D n equal 1 superspace which you're familiar with, and then just do a little bit of modification and see what happens. So that's very easy in a sense. In fact, there is a big exercise, if you wish you can do, big exercise, which is to repeat the whole book of S. Bakker textbook for 3D n equal 2. And in fact, this is actually an interesting exercise in the sense that most of the things are the same. You can take most of the formulas, except that there are some new things happening. So the question is whether you can find these new things.
And they do 2 dimensions.
yeah. You could do that same for 2 dimensions. And that will motivate you to think about what is chiral superfield and why does it only multiply, etc. There's all sorts of questions which you can ask. And that's right. And unfortunately, well, if this is a lecture, I must stop here and come back in the next lecture. But, but unfortunately, since this is a workshop, I can't do that. So I'm going to tell you some of the punchline in the process, but not everything. So I think this is a rather interesting idea, interesting exercise. Now, so let's start with the fermions. So in 4 dimensions, we have Q alpha and Q alpha dot, for example. And then we have this annoying alpha and alpha dots. So there is this important dot. And the reason that we have dot is that we have this, we have the symmetry, so silicon 1, which is related to, it's the same, it's locally to SL to R times SL to R. So this is the thing we run in the textbook. And so there could be representation of this, which is rather than alpha, and the dotted things represent another SL to R. So this is why you have this crazy dot here. Now, let's go to 3 dimensions, which is what I want to do. Now, in 3 dimensions, the counterpart of that is easy. So you lose 1 dimension. So you get rid of 1 coordinate. So we have SL to 1, which, if you like, this is SL to R. Oh, so there is just 1 SL to R. So there is just alpha. So which means that if you dimension reduce it, there is no distinction between alpha and alpha dot. So this one becomes both maybe I should use the same, both undot the same. So this is a huge difference. And of course, there are some basic monomorphics, which are chiral and vector multiplets, which is easy to extract from the textbook. And so let's take and it's almost the same. So chiral, so let's take a vector multiplet. So in a vector multiplet, in 4 dimensions, we have A mu, and we have lambda, and then the auxiliary field D. So this was the vector multiplet. And you compactify, so that means that one of these scalars, one of these gauge components of the gauge field become a scalar. So if you write this with the A3 in 4, so there is a real scalar. So this sigma is a real scalar. And then this chiral multiplet. Right, so this is two Majorana polynomials in 3 dimensions. And this is the chiral multiplet, so we have phi, psi, yeah, so this doesn't change much. Now, well, there's interesting thing happening in 3 dimensions. And one of them is that the form of the kinetic term for the H field. So in 4 dimensions, well, the kinetic term was written as d sigma. And well, let's see. So let's take throughout my lecture, let's take H group to be abelian, because that's what all I need. So that there is no commutator term. It simplifies the expression somewhat. So this is the gate group. In fact, all my flavor symmetries are abelian too, but that's not necessary. Right. So d equals 4. And then this could be written as W alpha, W alpha, W alpha. And W alpha was defined as, if I reflect it, there's a code or something in a conventional definition. And the alpha B, sorry, probably I should have prepared the notation B. This is the current multiplier, this is the standard notation. So this was the kinetic term. And this is still true if you dimension reduce. But in 3 dimensions, we can do another interesting thing. But this is still true in D equals 3 if you dimension reduce. But another way of writing that is that you have sigma squared, where the sigma is defined by x alpha beta, the alpha d bar beta, b. And it's a useful exercise to show that, for example, these two are the same up to partial derivatives. After terms, so after integrate over the whole spatial coordinate, these are the same. So there are more derivatives here, but that corresponds to the fact there are more integrals here, and the derivatives and integrals are the same. So you can check that. Now, first this is a superfield, and this superfield is actually interesting. And you can do this like the exercise of writing this in components, and then there is this real scalar in the bottom component, which is the same as this one. And then there are also terms like d sigma sigma mu sigma, and then f rho sigma, and there's u rho sigma. So you find that there is some interesting combination here, which appears. And then this thing is actually a very interesting combination. So let's call this, say, JB. JB. And the reason I call this JU, well, maybe if I write this, people in the back can see. Right. So should I cut off the horizon something? Can you see people in the back if I write here? Maybe not. Okay, but anyway, sure. So anyway, so this is okay. I could try to remember, but anyway. And so this is, let's define this JU. And the reason that this is good is that it's conserved quantity. So we have JU, JU. So we have epsilon mu sigma, and let's say mu f rho sigma. But this is 0 due to the Ampere. Or since I'm doing the Ampere case, you can just expand and check. So this is a conserved quantity. And typically, this one is called a current for the topological U1 J symmetry. And I'm coming to that later. But at least here at this point, this is just a current. So in fact, this is a current multiplet, a linear multiplet. So this is a multiplet in containing the current. So there is this interesting multiplet, and with which we can write down the kinetic term. Now, of course, there are many parameters, many more parameters, but many parameters in the theory. So in order to specify the theory, I have to not just the kinetic term, but also have to specify various parameters. So what are the parameters? Well, there are some parameters which are already present in West factor, and that's the parameters in the superpotential. And that's in three dimensions called a complex mass, for the reason that there will be a real mass, as I'm going to expect. Now, the complex mass is right, so is encoded in the superpotential. But by this I mean that I have the general case where there are multiple chiral multiples, phi 1 to phi n, etc. But I don't show the index enough to simplify the presentation. So so this is a holomorphic function. Cross conjugation. And then this could contain, for example, m squared, pi squared over 2, and let's write mc in order to stress that this is a complex mass. And I'm not going to use too much this complex mass, but at least this is a legitimate parameter. And then, well, there is one important thing which you can immediately see, namely, this is a holomorphic function. So the holomorphic actually works in 3-dimensional n equal 2, just as in 4D n equal 1. And that's important because holomorphic is the guiding principle for showing, for example, for non-renormalization. Not by side stick, right? So that's the argument in the 90s, and that argument doesn't have to use it's a diagrammatic complications, which is presented in this part. So holomorphic is a powerful argument. So holomorphic is actually still there in 3D n equal 2, which is a good sign. In fact, most of the discussion 3D n equal 2 crucially relies on this holomorphic. Now, but having said that, there is actually something real about 3D n equal 2 series. And that's this real mass. So what's this real mass? So the real mass is that there is d4 theta, and there is phi bar exponential b. So this is the usual kinetic term. So if there is a charge, we could have q, for example. Let's say charge is plus 1. Now, what I can do is that I'm going to give the vacuum expectation value to the theta squared component. Theta bar component, where this is a real parameter, which is called the real mass. But in the original, so if you regard this as a kinetic term, and then there are all sorts of different terms. There are fermions, etc., and this is just a sigma. In fact, this is the same as the sigma. But I changed the, so in the component file, it's the sigma, but I changed the notation to emphasize that it's a mass term. And originally, in the original kinetic term, there are many terms. But let's suppose that I'm going to set all the others to 0. And then just turn on the expectation value for this sigma, which is this m. And since sigma is a real parameter, that's the third component of the gauge field, so this mass is a real mass, it's real. And that's known as a real mass because that's also an exercise maybe. So if you expand in components, and then you could see that it gives rise to some expression like this, where we have epsilon alpha beta, phi alpha phi bar beta. So Lagrange contains the terms. So this is no other real. So that's why it's called a mass term. And one way to explain that is the following. So I could think of this as the Wilson line for background symmetry, global symmetry. Symmetry when we compactify from 4D to 3D on S1. Sorry, okay, so maybe I should have stated more explicitly. So what I assumed here is that there is a chiral multiple to phi, which is charged under the global symmetry. And this is a coupling to background global vector superfield. So in order to emphasize, I should write the background. So I wrote BGD in order to emphasize background. Right, so this is the background issue, and this is the background coupling. So if you incorporate a kinetic term for this guy, that becomes a gauge here. But here it's fixed as a dynamical, so non-dynamical background gauge. And the sigma plus the subcomponent of scalar, which is the same as the Wilson on incompatible. So you turn on the expectation value of that, which means that we turn on the Wilson. And that's why it's consistent with the 3D symmetry, but not in 4D. We didn't have this parameter in 4 dimensions. And in fact, this is a very interesting parameter because it means that it gives rise to new phenomena in the phases of supersymmetry. Namely, I said that previously there is a holomorphy. So when there is a holomorphy, the constraint is so strange. Everything should be complex. So in the parameter space, there could be something funny happening, but that should be consistent with the holomorphy, which means that could at most 4 dimension 2. But this is a real parameter. So if you change this real mass, so this is a complex mass. But if you change the real mass, it might happen that at some value of this real mass, things change dramatically. And in fact, it's known that even say, for example, if you study the dimensionality of the modular space, even the dimensionality of the modular space jumps dramatically if you change the real mass. So which is not there in 4D equal 1. So that's part of the reason that there are new phenomena in 3D equal 2, and that's why 3D equal 2 is interesting. Now, there are also other parameters which you can find in this one.
Are there non-local generalizations of this where you have operators at different points with the Wilson 9 connecting them?
Oh, okay.
Does that preserve all the symmetry?
Well, I think, well, of course, well, let's see.
Because that's an operator like with two charged.
Right. Well, of course, you have to supersymmetrize the operator, but I think if you supersymmetrize appropriately, I think that's probably the case.
So there's a non-local.
Yeah, I think so. I think so. Yeah. Maybe I should add, as a scientist, I never thought about that, so you never know. so let's see. Right, so and then there are other parameters in the structure. That's this A5 parameter. Right. This A5 parameter. So what's this parameter? So that was a term. Right. So that was a term like the probably it's kind of well. In this lecture, I'm not worried too much about normalization. So, but let's say, for example, right. Sorry. So this sigma, or maybe the more familiar form is D for B, and you can do the partial integration. So this is the term, but so this is the Fi parameter. So this real, sorry, zeta is a real parameter, which is a Fi parameter. But you can also write it as follows. So d squared theta, and then there is a v background. Oh, okay. So if you want to write this, you have to deforce it. Well, maybe I should write this 1, and then the background part is equal to 1. So this is just a rewriting. So I introduced this two theta part, theta and theta part, so that counts as this interval. So I start with this expression and just rewrite it this fancy way. And the reason I wrote this in fancy way is that this combination is actually the same for supersymmetrization on the Chern-Simons term. This is also another term which is specific in 3 dimensions, but not in 4 dimensions. So there is a Chern-Simons term which appears in Simon's law, And the Chang-Sang's term, well, of course, the botanic component is FHTA maybe minus the bar lambda plus 2b sigma, if I remember correctly, the K over 4 pi. So this is the supersymmetry relation. K is an integer, so that's no other level. And recall that this D is the auxiliary field in the vector multiplet, and sigma is the third component scalar, which is the same as this sigma, which I did here. So this sigma is actually very crucial. So I should probably emphasize this. And one avatar for that is this material. But another avatar is this FI parameter. Now, right. And then this can be supersymmetrized. And if I get the coefficients correct, and then it takes the same form. Where in this case, this is the D and sigmas are the linear multiplet and the vector multiplet for this super. So this is actually very similar to what we have here. And this is called a diagonal Chang-Simons. And this is called off-diagonal Chang-Simons. In fact, if you have many such things, I could be ij, ij, and then there's some of ij. Okay, maybe I should have. Right, so, for example, you could write down such stuff. Where I and j runs from something. In the case, the symmetric metrics. So, so if you take the off-diagonal component, it reduces to that.
Sorry, why is off diagonal?
It's why it's off-diagonal because it's off-diagonal with respect to this matrix Kij. Namely, right. So what? Right. So maybe I should have said. What I mean by this is, well, in my case, right. So I said schema, very schematically. That is, in fact, that's a good point. So V1 to Vn, so there are many U1 symmetries. But suppose that part of it is gauge symmetry. And so that's a dynamic one. But suppose that the others are global symmetry, so they are background U1 gauge symmetry. And then, if you take this to be background U1, and this to be dynamical U1, and you have V background times sigma. And that's the term you have here. So when I write this, so that's in fact the elegant way to formulate things. So there are global symmetries and right. So background global symmetries and the gauge symmetries, but they are almost on the equal footing. The only difference is whether they have a kinetic term or not. So they are on a very equal footing. Right. Now. Oh, okay, so there is a right. And now I could connect this story to that one thing I said previously. There is this topological U1. So again, well, since I made it to be right, so let's write this down in components. Right, so I start with a single U1, but then I consider the case with multiple U1s and I wrote down more generously. So let's go get back and then expand again in components. And of course, what you obtain is that A1 HTA2. So this is the off-diagonal Chang-Simons, which is one of the components of this expression. Now, it's an exercise in this differential form. Well, I could write it down more explicitly. Well, let's forget about the coefficient. And then this is F. So field string F2. Now, so what is quantity? So maybe I should go here. And the quantity here is that A1 of mu and F2 rho sigma. Or maybe I should. And then there is a mu rho sigma. So that's what happens in differential form. But then it happens that there is this definition here. So there was this definition J mu. So this is actually A1 mu J mu. Well, J for 2, so maybe I should write J And this is the well-known coupling between this symmetry, I mean, in this case, this U1 topological J symmetry, and the dynamical activity. So this is the coupling. Well, in this case, U1, U12 to current of U12 to U11. Perhaps I should eliminate this. And I put this 2 to be this topological U1, and this to be the original one. So the conclusion here is actually this off-diagonal Chern-Simons term. So off-diagonal Chern-Simons term could be written as this combination, which is a off-diagonal Chern-Simons, off-diagonal Chern-Simons. But that one, oh sorry, not well. So maybe this is off-diagonal. So probably I should write this way, such that this is off-diagonal term. Sorry about that. But this off-diagonal contribution is a complete. And then you can compare this to what happens here. Here, in this case, there is a symmetry, which is U1. And if you give a bet to the scalar component of the multiplet, that was the Yamazaki. Now, here, in this case, you have this U1 symmetry, and you couple it to this U1J, which is associated with this curve. And then, if you give a bet to this background delta view, and then the expectation value is the Yamazaki. Sorry, the F5 parameter. So the story is actually completely parallel. The only difference is that the U1 symmetries look different in the Lagrange. On one side, this is so symmetry in the Lagrange, and this is also a symmetry with the Lagrange, but it looks different. It's associated with the shift of the photon, UR photon.
Is there a possibility to generalize this to non-obedient version? I mean, I know if you turn on the mass, you break the non-obedient phase symmetry.
Yeah, I mean, I would say that, for example, if you want the real mass, for example, I can only, well, essentially, it's sufficient to turn on to the diagonal part.
Right.
So, yeah, right.
So there's no way to.
Yeah, I mean, one explanation, which I think is true, is that in this case, I'm compactifying S1. So I have to, right, so I think about the Wilson line on S1. But the fundamental, right, but the fundamental group of phi1 is abelian, which means that you can simultaneously diagonalize. And so maybe you worry about the, well, okay, so no problem. So simultaneously diagonalize, so you can, the only possible values are the diagonal elements. Right? So you can turn on this only in the curve with respect to the curve time. And that fits nicely with this localization computations.
Yeah.
In fact, these will be the parameters of which you integrate in localization, and that's also with respect to the curve time.
Yeah.
Right. So let me try to recapitulate what I said so far.
I guess that what I'm trying to say is that make a non-obedient mirror symmetry a lot more trivial.
Yeah, I mean,
Because you don't have all this nice manipulation we have are really kind of obedient mirror symmetry.
yeah, that's right. So yeah, I mean, right. So I mean, that's right. So well, of course, people discuss the modular space of 3D and non-abelian series. That I mean, the mirror symmetry part is not be too much developed, except that for example, there are some examples of the abelian versus non-abelian dualities in 3D series, which people conjecture and verify this partition function, like a duality appetizer or things like that. For example. So there are examples of that. So hopefully we have a better tool than 15 years ago, so we could tackle the problem. Right. So yeah, that's right. So let's see. So let me try to recapitulate what I said. So this is just really the 3D version of this matter, but importantly, gradient, Chern-Simons, real mass, etc. And you see that interesting structure here. And what I mean by interesting structure is that there is some similarity